Now we're going to do an example on related rates. We're going to start with a simple equation, y squared equals x cubed. Now I want you to imagine that both variables depend on another variable, t. So there is a function x of t, which we don't know, and also a function y of t, which we don't know. Since both variables depend on another variable, they will both have derivatives, dx dt and dy dt. Now we are given y squared equals x cubed, and we are also told that when x equals 1, dx dt is equal to 3. And we're looking to find dy dt at that point. And we also know that y is greater than or equal to 0. First, we need to differentiate the function, and the chain rule is the most significant differentiation rule here that we're going to use. First, we have y squared equals x cubed. We bring the power down, by the power rule we bring the 2 down, and we have 2y dy dt, which equals 3x squared dx dt. dy dt and dx dt are there because of the chain rule, because we're taking first, using the power rule, the derivative of something that has its own derivative, which is why we need to include dy dt and dx dt in the differentiated equation. Now we're going to find y at the point that we're given by using the original function. Y squared equals x cubed. We know x equals 1, so we substitute that into our equation. We have y squared equals 1 cubed. And 1 cubed is 1, so we know y squared equals 1. Now we have y equals the square root of 1. And finally, y is equal to 1. We know it's not negative 1 because we were told before that y was greater than or equal to 0. Now we have 3 parts. X equals 1, y equals 1, and dx dt equals 3. Now we can use all of these in our differentiated function. So we plug those in, and we have 2 times dy dt equals 9. Now divide that by 2, and we have dy dt equals 9 halves, which is the answer to our problem.